In this session, we're going to discuss probably the most important concept in mechanics of materials, which is the concept of stress. And basically, we are interested in two types of stress that are commonly found in materials and structures, normal stress and shear stress. Both of them are basically a manifestation of the same idea, which is a force divided by an area. In the case of normal stress, the force is acting perpendicular to the area. So this involves tension and compression. And in the case of shear, the force is acting parallel to the area. And so this is the kind of stress we get when we have torsion, when we have shear forces acting on beams, columns, friction, etc. So I'm going to give a few examples of how to apply these simple concepts, and then we're going to build upon those on later sessions. Let's give an example of normal stress. Say you have a simple structure like this with two bars connected, welded at their ends. This one has a diameter of 2 inches, and this one has a diameter of 1 inch. And at the end here, this is subjected to a force P of 10 kips. We are interested in computing the stress, the normal stress, through this cross-section, and then the normal stress through this cross-section. This cross-section is larger, so it will have lower stress. This one will have higher stress. So in this case, for this one, we would have 10 divided by the area, which is pi diameter square divided by 4. If you do the calculation, that comes to approximately 12.7 kips per square inch. Right? So this is the cross section of that member right there. Now, across this cross section here, the stress, the force is the same, but the area is different. So the stress changes. In this case, we get a stress of 3.2, approximately 3.2 KSI. Right? Now, there are some stress concentration effects that take place at this connection. We're not going to discuss these at this point, but they're very important and they need to be considered. The way to calculate those is you can use theory of elasticity, or you can use finite element modeling to try to compute the stress concentrations around this point. And the reason that it happens is because this stress is coming in here, and this one becomes uniform up here, right? So between those two, there is a transition, and there are some other more complex states of stress that happen around this connection, and we're going to talk about those later on. But at this point, basically, we are interested in the mean average stress across these different cross sections, right? So very simple, just divide the force by the area perpendicular to the force. As an example of shear stress, consider a connection that looks like this. Imagine you have two elements connected with a bolt. This is looking from the side. If you look from the top, you find something like this. right, and the bolt is going right through that. So this bolt here is in shear. If we have, let's say we have 5 kips here, and then 10 kips pushing that way. That bolt right there is subject to a shear force. Now, if we do a free body diagram of that bolt, we can see relatively easy that we basically have a force here, a force here, and a force like that. This is 5, 10, 5 kips. The shear right here at this point is 5 kips, and the shear right here is 5 kips as well. So basically this 10 breaks up into 2 5s, and that's the shear force you get there. So V is 5 kips, and let's say this bolt is 1 inch diameter. So then the shear stress becomes 5 divided by pi diameter square divided by 4, which comes to approximately 6.4 KSI. Straightforward. So normal stress, again, when the force is acting perpendicular or normal to the surface. Shear stress, when the force is acting parallel to the surface. And in both cases, you divide the force by the area to obtain the average mean stress.